Hello, everyone. And thank you for joining us, actually. I'm glad to be here and talk about, guess what? AML and MLOps. Not alone. I have Burke with me. Thanks for joining us. What's the topic of discussion? Let's see.
Hey Andrea, hi everyone. Super nice to be here. Yeah, the topic: optimize your ML workloads on Kubernetes. That's a hot topic, isn't it? Currently.
Indeed, it's a hot topic, and maybe it's worth covering a bit of the agenda. It all started with a use case that I'm going to go more into details. And then we're going to talk a bit about the challenges that the AML world has if Kubernetes is actually needed and helpful for that. And what are the optimization opportunities that we have when it comes to machine learning workloads with Kubernetes. Then we'll move towards some key considerations and an end-to-end solution on how do we see it usually run within enterprises. And last but not least, some learnings as well. I will not make it any longer, and I will already start with a use case or story that that kickstarted this thread of thoughts actually. And when it comes to the public sector, there is a high investment in machine learning these days. We often hear about what is called AI sovereign clouds, and there are a couple of interesting aspects when we look at that. There's a clear focus of the public sector to move towards open source. What comes to mind here is, for example, the latest announcements that Switzerland, I think, did, for example. But then also they're not called sovereign clouds with no reason. They have a large number of nodes, a large number of team members running, which are divided between different teams. And it also comes with a clear need to ensure that the hardware is not underutilized underneath, but also that there are clear security guidelines. You don't want all the data around your patients within the public sector to be shared amongst all data scientists, for example. Probably there are teams specialized with it. And circling back to this, the fear of underutilizing the infrastructure, but also the need to avoid buying further hardware is what challenged in this situation the public sector organization to look at optimization opportunities of their ML workloads. They do run on Kubernetes, and that's why I have Park with me today. I already briefly mentioned that they run on Kubernetes, but what's interesting about such a use case is that they use also a wide spectrum of cloud native applications. They store their data in, on one hand, MySQL and Postgres databases, but then they also look at NoSQL solutions such as OpenSearch, for example. And then they use, or they do data processing. It's safe to say that they use Spark for that. And last but not least, we go towards their core of their activity, or what triggered the build of such a large ML infrastructure, and it's training models, developing models, and then deploying them to the edge. That's why they use tools such as Kubeflow, for example, for training models, and also for experiment tracking on model registry, feature stores, data visualizations. And that also brought another challenge around how do we integrate such tooling. But that's not what I will focus on, at least today. I'll focus on the other challenges. And the first one that I briefly touched upon is the computing needs. A high number of organizations, a large number of data scientists, and the clear need to optimize the computing that already exists and ensure that the objectives are reached and the investment is not almost lost. But then also there's a need to have flexibility on how resources are assigned, because moments when we do, for example, model training is different. Um, Maybe you have something, or you have a project running on today, and then you train more for the next 3 months, and then it just goes into maintenance mode and it needs less training, for example. And then about the underutilization of the infrastructure, there are studies actually on the market that we have around 60% of the infrastructure of the hardware is underutilized. Yet organizations are waiting for months and months to get delivered new hardware. Now, with that being said, and with the caveat that they use Kubernetes, I still want to ask you, Perk, is Kubernetes always a good fit when it comes to machine learning workloads?
Thanks, Andrea. That's a very good question. And the example that you've shown, it is only a one use case, but I believe that we've seen it, over and over from multiple customers, which actually had, the very same problem. And what they usually ended up doing is using a Kubernetes there. And why do they do it? That's a very good question. Like, why Kubernetes? Why just not do virtual machines or just bare metal servers, right? So if you think about it, and if you could switch the slide, there are a couple of areas why Kubernetes might be the best one there. First of all, it is quite ubiquitous right now. You have a lot of information how to run your workloads. You have a lot of knowledge within your teams already how to use Kubernetes and how to run workloads on top of Kubernetes. And this is something that we should not forget about. It was not the case before. Everybody could run their workloads one way or the other. Some people, some companies just use, like bare systemd. Some companies just used containers and run them through Docker, through Docker Swarm, or just run those containers by hand. Other used VMs. So that was like free for everybody used something else. With Kubernetes, everybody has the same spec to run things, and that helps a lot, because now you can have a conversation about running things and making them actually run better, to better utilize things, because you are talking about the same specification. Another aspect of that would be that Kubernetes itself is an expandable platform, and but what I mean by that is that when you have your Kubernetes cluster and you would like to add something to it, it is as if you've created your, as if you've made your Kubernetes fit for purpose, right? So you've added some functionality, but it feels like this functionality was built for just for Kubernetes, right? It doesn't go out of Kubernetes. So, for example, when you add operators, those operators are configured through custom resources of Kubernetes, and it feels as if that was a part of Kubernetes, from the very beginning. Another thing I think that is important here is that Kubernetes was purpose built for clustering, from the get-go. And that is not something that you get, a lot. Previously, obviously, we had big clusters of computers and supercomputers, but those are still available only to big organizations, scientific organizations who have the money, right, for this. With Kubernetes, everybody can create a cluster. With our Kubernetes, for example, with micro-K8s, building a cluster is just K8s bootstrap a cluster, and then you just K8s add a node. You just join them together, and you have a cluster, right? And the Kubernetes itself figures out everything for the clustering. That helps tremendously because it is, I believe, it is super important for AI and ML jobs to be able to run in a clustered environment, because you can make them fit better in that way, right? Because AI ML jobs they usually don't fit a single server, right? They are having a huge memory resource consumptions and compute resource consumption. So if you are to run those jobs, if you are to run those tasks, you need a lot of compute, and you just cannot get it from a single computer. And last but not least, the community and the industry is there, right? So there's a lot of software and there is a lot of hardware that target Kubernetes, and by that I mean that companies who create the hardware, they target Kubernetes usage. So it's not like you just get the hardware and then now figure out how to make it happen. You get the Kubernetes as a built-in from the get-go, which is very, very helpful. And also if you have a huge user base, it means that usually someone has already solved the problem, right? It is rarely that nobody has seen this before. Not in the Kubernetes community anyway. And because AML is only one of the possible usages for Kubernetes, and in a very, if you think about it, on a very deep level, those AML jobs, they are no different than any other jobs. At the end of the day, they are like containerized workloads. The problems that you might get with clustering itself, how to run your jobs, are the same for everybody, right? So there's a huge chance that things first will work, and if they won't, then that you already have your solution there.
There is something that comes to mind actually, Berg, that I strongly believe actually that in the long run, most of the Kubernetes jobs will actually be related to AI/ML, but maybe that's a topic for another webinar. What I do want to ask you is, do we truly need to optimize anything, since Kubernetes is obviously developed enough and advanced enough to run these jobs and to leverage the infrastructure underneath?
Yeah, I think that's a very good question, Andrea. Thanks. What you know already is that what we saw, out there in the wild, the worst utilization that we've come up with, that we've seen, was around 10 to 15%. So if you first buy, the super expensive hardware and then your utilization is on the 15% level, then it's no good. Nobody is happy. The average utilization is around 50%, right? And it still leaves a lot of room, and it would be better if you could do better there. When you optimize, you can go as high as 80-90%. That's what we were able as company to deliver to our customers. So if you optimize, and you can optimize on a couple of levels, and you get 90% of utilization, then you're really good. And what I mean by the by this optimization, first of all, you need to know that you need to optimize in the first place. Like, right? How do you know that? And for me, the obvious answer is the observability. You just observe your hardware, you observe your software, and when you do that, you can see that you can optimize on a couple of levels. Like you can observe your hardware, you can observe your Kubernetes itself. You can also observe the job, right? So for hardware observability, you get this information from the hardware vendor, right? And then you have tools that are specific to the hardware. They give you information about the memory usage, about the GPU usage, and you get those through the operators usually. Then for the case itself, you can get it through the usual, observability tools like OpenTelemetry, for example, because you need the usual information about how your Kubernetes cluster is doing. But then interestingly, there are also specific libraries for your data, right? For the jobs themselves.
I think
So
it's sorry. Go ahead,
no,
Per. You know?
no. I just wanted to add that there are those libraries that, for example, stream out from the OpenTelemetry, like OpenLLmetry, and this is very good because now you have the ubiquitous way to observe how your software is doing across the whole stack, from the libraries through the scheduling to the hardware.
I think what you mentioned the monitor the observability needed for Kubernetes, but I think what we should really focus on is ensuring that we have an end-to-end observable infrastructure, whether it's you use bare metal, you use public cloud, you are on-prem and you use OpenStack, for example, and then you run other container orchestration solution on top and other cloud native applications. I think they should all be observable. And on one hand, they enable us to have or to identify optimization opportunities, but they also ensure the continuity of the work. But beyond that, and often it's seen as an afterthought, we should ensure the observability of our models, that both when we are building them as well as when they are running, and of the data itself. And you already brought that up.
It's
Before I
very good.
deviate,
Yeah, sorry, it's very good that you've mentioned the continuity, because you cannot just observe at this point and then just forget about it, right? Like you have to do it constantly. The observability thing is like you have your cluster, you observe how it's doing, then you make your optimizations, but then after a couple of months, not only your teams change, the projects that you work on change, also the tooling changed, and everything could be different, right? So the observability is a crucial thing that just needs to be there the whole time to be sure that you are actually optimized.
but let's now derail this conversation part and focus on Kubernetes. Why Kubernetes for AML? And you're the expert here, so the mic is back to you.
Thank you. Okay, so there are a couple of things that make Kubernetes special for AML, and there are a couple of areas that you have to make sure are taken care of. First of all, obviously, you need to have the hardware, right? The specialized hardware for your AML jobs, so that those jobs which are, and you can tell me because you are the expert about it, but they require specific mathematic calculations, matrix calculations to be more specific. Also, it is highly parallelizable, right? So the hardware needs to support that, and you can get your support for the hardware through Kubernetes, because providers of those hardware, that they target Kubernetes, in the first place. Then you need to make sure that the networking also is working, because what makes the use case special here is that I think that many times people don't realize that the GPU to GPU traffic it can be really high, right? This can be really high volume of traffic, and it needs to be taken care of properly so that you just don't starve your GPUs because they don't have the data that they need, right? Additionally, you most probably need to have a dedicated storage, right, for your AML jobs, and Kubernetes helps here a lot as well. And last but not least, we'll mention that later on. Kubernetes helps with the job scheduling because AML jobs have quite special scheduling needs. It's way better if you could schedule on the low level, right? You need to be smart how to queue the tasks. You need to be smart how to schedule your workloads wherever the hardware is, really, right? And there are specific optimizations for the Kubernetes there as well. If we go to the GPU operators, let me just briefly touch on how this is done, underneath. So obviously, let me go from the bottom. You need to have the hardware, right? So you get the hardware. You have your compute unit, whether that is a cloud instance or in your data center. You need to access this hardware somehow, right? And most probably you will be using the Linux distribution and Kubernetes on top of that. You need to load the drivers. That's where the GPU operator comes from. The GPU operator can come from different vendors. Specific hardware vendors provide you with the hardware and the GPU operator, the software. The software can do the discovery, for example, of what hardware is being there. So if you have multiple nodes, you can run your operator, and the operator will label those nodes that, hey, here is this GPU, here is that GPU, you have those features, here you have the other features. And based on that, you can be smart how you run your workloads, right? Also, this operator, once it discovers the specialized hardware, it can load the kernel modules, for example, to make the hardware available in the first place, right? Additionally, it will add you the monitoring, the hardware level monitoring that you need. And it will expose those features to you so that you can use them.
One
So
thing
that's about
that
Oh yeah,
One thing
sorry.
that I think we should mention about the GPU operators is that they are tightly close to the silicon vendor, and when we think of it, the market is evolving, and probably each hardware producer has their own, and Kubernetes should be able to efficiently work with all of them. Am I correct in this statement, Perk?
That is true. That is true. That is on the vendor. But on the other hand, I believe that the use cases for those jobs or AML jobs are so vastly different that unfortunately you will always have to make sure that your cluster is being utilized in a way that you want it to be. I don't think that there's that it is possible to figure out all the different use cases that you could use your hardware for, and hence be super smart on the vendor level. Even though obviously there are like it can be better, it can be worse. There are vendors who are more advanced. There are vendors who are less advanced. It is progressing though, so it is better and better with every new generation of the hardware and the software. But I don't see that happening. I think that there will always be this human element to there.
Okay, and I guess the GPU operator is not the only one that we should think of, right?
Exactly. So the GPU operator just gives you access to the GPU that you might need, And I say that you might need because you could. There are types of jobs that you could do with CPU, right? So you don't always need the GPU. It's just better fit for purpose for the specific matrix calculations and highly parallelizable jobs. But there is nothing that stops this to be run on top of the CPU. But going back to the other things, ideally you would also have the network operator for the specialized network hardware as well, and that is because the network is key. You need to make sure that your AML jobs are not starved for data, and that they can write the data fastly, right? And that they can do the calculations based on the data that is available, in the other GPU, for example, right? So this can be, well, this is doable if you have multiple GPUs in a single compute. It is sort of doable if you have them in the single rack, but more often than not, you don't have only a single rack. You have multiple racks. Those racks can be in different places, right? You can have those in multiple departments, for example, right? So you need to make sure that the network is fast for them. Otherwise, you will see a lot of slowdowns, and your GPUs will just stay unused, right? And for those, you have the GPU. Sorry, not GPU. You have the network hardware, and the network hardware needs to be managed as well. So you could utilize the network operators as well. The difference between the network that is being used for like usual Kubernetes workloads and the AIML workloads is that, like you can see here, the normal Kubernetes workloads are mostly loosely coupled. Those are loosely coupled applications that just speak to each other more often than not to the HTTP. Here for the AML jobs, you have very, very tightly coupled processes that can that know about each other so much that they can speak together and have the direct access to their own memory, right? They can do that. They can be super fast when they do that, but for this they just need the network. And for network possibilities, you have a couple of options there. If you could switch the slide, thank you. There is ROC, right? Traditionally used for it used the normal network, right? But it was quite slow, so that was RDMA between the so this is direct access between the GPUs. But because it was slow, then we had the InfiniBand from NVIDIA. It was good, but it was proprietary, and it just needed specialized switches, right? So it was not like everybody could use that. It was working very well, but right now we have this new thing called Spectrum X that is Ethernet based, so everybody can use whatever switch they want as long as it is very fast. And when you do that, that is a good option for your networking between the GPUs.
And go ahead.
No. I just wanted to ask you to talk about a little bit about those enhancements.
I think when it comes to opportunities of optimizing, the first thought is Kubernetes, and that's correct. There are tons of optimization opportunities around Kubernetes and tons of enhancements. But the truth is that most of the machine learning workloads, they run on top of Kubernetes using some machine learning operations platform or some tooling, let's call it this way. I don't want to define it necessarily. And there are opportunities there and enhancements there that are worth keeping it in mind. And if you look at the AI workflow, of course, the initial step is building. How do you build models? What do you need from the operating system all the way to the packages that run on top of it? there are capabilities that we should bear in mind. And when you build models, often you don't think of how to optimize it, and that's a second step, and it's a separate step. On one hand, you can optimize how they're being trained and how they're being developed, but also how their size, for example, and that should go hand in hand with the hardware underneath. We see, for example, here a trend in organizations optimizing different famous frameworks such as PyTorch or TensorFlow to better run on their own hardware. And that's something that whenever you work with machine learning workloads, consider as well as try utilizing. But then there are also different frameworks that are specialized for different use cases. And here I think of computer vision, for example, it's quite a famous one. There are frameworks, for example, like Mindscore, who are is really optimized for such a use case. And if that's what you're working on, some computer vision use case, there is nothing that should stop you from trying it out. And then we have the maybe the last side of the machine learning lifecycle, which is deployment and maintenance of a model. There are different optimizations capabilities there. Often, for example, organizations are reluctant to using Kate there, and it's a lot of discussion on how do we do that. But also at the same time, if you have for example, an NVIDIA Jetson, you should really consider using your Triton as a model inference tool, and you should consider using Triton inference server rather than anything else. And we have previously discussed about AI at the edge, so I will not focus that much on that side, but today I'll focus more on the optimization part, which is where we are. And if I think of an MLOps platform such as Kubeflow, which we've been investing on in the last years, I was about to say couple of, but they're way more than 2 years since we invested in Kubeflow. Um, Kubeflow stands out, for example, because of its component, which is called Katib. And Katib itself is used really to optimize models and through different techniques such as hyperparameter tuning. That doesn't necessarily optimizes the resources, but rather leads to performance. And that's where the fine line is, because that is a technique and there are opportunities there, but it doesn't necessarily mean that you optimize the resources in the short term. However, I think you will reach the performance, the desired performance of a model faster, and you will avoid doing training and retraining several times, which at the end of the day is an optimization, even if it's not the first thought. And however, the capabilities go beyond this, because if I think of the training environment, and probably I think Jupyter Notebook is the famous one on the market, um, we should definitely consider how do we train models in an optimized manner, and then how do we optimize the models. But then we should also think, how do we automate these machine learning workloads? One of the challenges that organizations face is the large amount of manual tasks that often comes with machine learning, which is kind of counterintuitive, because you do machine learning to automate tasks. Yeah, machine learning sometimes is very manual. So I think automating your machine learning pipelines, which tools such as Kubeflow pipelines, is going to optimize the resource utilization. It's going to optimize actually the velocity to which you reach a model that is production grade. But then also, how do we process the model? And that's where tools such as Spark comes in place, especially for use cases when there are large volumes of data. What comes to mind now are retailers. They generate a lot of data and they need to process it quickly. Often the expectation is real time, and that's where the need of such tools is important. But then also when it comes to inference, on one hand, you need model serving capabilities. And if I go back to the example of the retailers that I just shared, you need model serving capabilities that meet the needs of the customer or the needs of the use case at the end of the day. Is it real time, for example, or does it run in offline environments? There are often situations when you have models or you have devices at the end of the day that are very remote and they need to be reached with the model. And last but not least, here it's important to mention the need to update the model. It's not a one-shot process. And what organizations should consider doing is building pipelines or doing models, having model serving capabilities that enables them to update the models whenever are needed in an automated fashion. Because otherwise, it goes back to the manual work that is time consuming. When it comes to operations and optimized operations, of course, we should use frameworks that are optimized for different silicon vendors. The Triton Inference Server is just one example. But then also, especially for the use cases where there's a lot of data being collected, there's a question on, is all the data necessarily? The short answer is no, most of the times. And doing some data preprocessing, understanding which is actually the data that you need to collect and how do you optimize or how much do you preprocess it at the edge before you send it to the data center is going to ensure the optimization of the storage, the training time, and so on, which are important capabilities if you think of how do we actually optimize our workloads and what does it truly mean. And if I'm being honest, that's not all. And I'm trying not to make it or turn it into a machine learning lesson or cloud native applications, because I think everyone was curious and passionate about the Kubernetes layer. But Paddle, which is at the end of the day, one of the capabilities that Kubeflow community introduced in the tooling, is a framework that ensures the optimization or ensures the ability of organizations or users to run distributed jobs. It's dedicated or it's very useful for deep learning and of course, again, also computer vision. And what makes it interesting is that it optimizes the way that jobs are distributed at the cloud native, at the application layer, which is quite exciting, and it reduces the time needed for smaller jobs to be fit in and to make them happen quickly. Yet, it almost, one question that I get often is this a job scheduler? The short answer is no, it's not a job scheduler, and it will never be. But it ensures that jobs are distributed in an efficient and effective manner, depending on their size and computing needs. Yet, do we still need a job scheduler if we have Paddle? Park, what do you think?
Of course, of course. If I may add one thing to this, is that even if we have the greatest job scheduler, it will do better if it has the smaller jobs. And I believe that here's what where Paddle actually comes into play, and it helps with the scheduler itself. But that being said, the scheduler has to be aware of the jobs that it's running, right? And the standard Kubernetes scheduler is just not GPU hardware aware. That is the biggest problem here. So we could use Volcano, which is another scheduler that you could just add on top of your Kubernetes, and to make it work better in this environment when you run a lot of jobs that needs to be aware of the underlying hardware and how to utilize this hardware. So we have Volcano, and it can do a couple of things that are like smart ways to make sure that your jobs are being properly scheduled, and in a way it will make your hardware be utilized better. One of those, for example, is that you only schedule a job whenever there's so many tasks. There's a threshold for the tasks that they will all fit to a node, and that is super helpful, because if you have all the tasks on the same node, they use the same memory. You don't need to go and pick the memory bits from the other parts, which means that your job in a way fit in a single compute, and that makes it finish sooner, right? Then we can have another one. We can also prioritize differently, right? So for example, Volcano here can prioritize jobs that require fewer resources, and that also helps because if we see on the next slide, when you prioritize jobs that do not need so many resources, you can first utilize the nodes that are already being utilized. And why that helps? It's a very good question. It helps because you never know what will be the biggest job that you need to serve, right? So you want to rather fill in your nodes to the fullest, possible amount, so that in a way you're prepared to run your bigger tasks should they happen. If you have the bigger task and then you just place it on a node that can take it. Otherwise, you will not you would not be able to do that, right? So that is another technique. And for example, and you can also have something else which is called the resource pools. You just have queues for your tasks, and you prioritize those that use the lowest resource utilization. But we have something else as well here. So we talked about the making jobs smaller by themselves, about chopping them to have smaller tasks. We talked about scheduling those tasks on top of your cluster, but then also you can have Armada to utilize your multiple clusters. So if you have multiple Kubernetes clusters, you can use Armada to place those jobs on top of those multiple clusters. That is a very important feature because more often than not, even in a single organization, you can have multiple Kubernetes clusters. So we see this in the wild. You very rarely have a single, huge Kubernetes clusters with 5,000 nodes. Not many companies do that. Rather, everybody is doing small clusters per team, for example, or per business unit. But then, if all of those have a hardware, you would like to utilize this hardware, right? And then imagine that there is a team that uses this hardware on a specific days, and then it just lays, and it's not being used. Then you can, without changing anything in your infrastructure, without changing anything with your clusters layout, you can just utilize those other clusters. You add the Armada agent, Armada executor to those clusters, and then you can schedule those jobs on those other clusters. And this way, you can utilize again your hardware that you've already purchased, and get better bang for the buck, right? That you've already used. But yeah,
Sorry.
what about the end-to-end solution?
I think when it comes to Kubernetes, I think it's really the glue of an end-to-end ML solution. Organizations these days use different types of GPUs in order to, or different types of silicon vendors in order to train models to develop their ML workloads. And often they use bare metal, but there are other situations as well when they use OpenStack or they run directly on the public cloud. However, most of them, when it comes to ML workloads, they run Kubernetes on top. Whenever they move away from POCing and MVPing, which often happens in environments that are definitely not standard, enterprises then adopt Kubernetes for their ML workloads. And in order to think of an optimized end-to-end solution, I think we should really think on how do we optimize it across all layers of the stack. I'll start from the top, from the cloud native applications that enable machine learning projects to scale, and that may be selfish because that's where I have more expertise. And then I'll go down the stack. We need to ensure that we can build pipelines. We can use frameworks that are optimized for different hardware vendors. We can use, and we have access to frameworks that are optimized for different use cases, such as computer vision, but also that we can leverage libraries such as Paddle to ensure the ability to run distributed jobs. But then when we go to the Kubernetes layer as well, Kirk captured a lot of the probably key considerations we need to ensure that operators are there. We need to ensure that we have job schedulers. And these are just some of them. But then I think we should always look at it as a whole. If you just optimize your Kubernetes and don't look at any other layer, you will get better results. But it doesn't mean you have an optimized infrastructure. You should really look as an organization on how do you optimize across all layers of the stack. And that's an iterative process, because as your ML workloads are going to grow, they're going to evolve, you're going to have more needs to optimize as well.
Yeah, that's a very good point. This has to be done, end to end, and also it has to be done, over and over and over again, because like we said at the beginning, you can start, you can optimize, and then this optimization will just go away over time, right? We have a couple of learnings about our, optimization efforts, right?
I think that's where they are.
Exactly. Thank you. And let me go into those just a little bit. And what was what was interesting here is that one of them, and this is something that comes every now and then, often, is that there is a human factor. You just got to listen to your team, right? And not only data scientists or ML engineers, or just developers who are enthusiasts and are interested in running things, and you have to slice your infrastructure in a way that everybody can use the hardware. But also there can be like compliance problems. They can be legal problems. Sometimes you just cannot run your ML jobs on the same machines that other people can use, because the nature of those workloads means that sometimes you can have the access to the data of the other people, and this is something that has to be taken into consideration. For example, when you slice your nodes, right? Then for the hardware, we've learned that you have to use the usually you would buy the very powerful GPUs to run your workloads. But what we've seen is that if you add a couple of mid-range GPUs, for example, you can make your scheduling more efficient. And then if you add just a little bit of low-end GPUs there as well, that gives you good, flops per dollars ratio for inference, for example, or some testings, right, tests, or some small jobs, then the optimization can go even higher. So what we've ended up doing at some point in a customer environment was to use the 70% of the powerful GPUs and 20% of the mid-range and the 10% of the low end. We also saw that the VMs are there. They are still there. They are going to be there. They are used for databases, for example, to pull the data that you want to run your you build your models against. There are some legacy workloads, and what we saw that was that the legacy works very, very well here in this scenario, especially when it is coupled with the mass resource pooling. So this way you can get some advanced features for optimization of your infrastructure. Then for the storage, we learned that you need to have different types of storage. You need to be aware that there are different types of storage to be used there. Not only S3 or object store from your cloud, but also you need to keep the local storage on your nodes, sometimes to use as a cache. Also, you need to have the big file storage, the NFS. You need to have the storage to feed your model, for example, to get the training data, and the storage has to be fast, right? And to get it fast, you need to have the networking, which can be a bottleneck, like we said previously. then what we've learned was that the Spectrum-X is a must with the latest NVIDIA GPUs, for example. And you just need to have the dedicated network for this GPU to GPU traffic and for storage. Also, your automation tooling that you might have needs to be aware of the top of the rack switching. And it needs to be able to reconfiguring, depending on the workloads that you run and depending on the traffic that you have running currently. And last but not least, we talk about it, but for the scheduling, the Volcano plus Armada plus Meek, for example, that can solve many problems of yours. It can give you quite good utilization. Like you said, Andrea, Kubeflow helps here, right? With the to control this with these pipelines, and with Paddle, right? To make sure that your jobs can fit and are smaller. And when we use this scheduling scenario, we were able to usually go from around 50% to even 80% or 85% in a huge clusters that use like 3,000 GPUs, for example. But apologies, I skipped a slide.
Yes, but being cognizant of time, Park, I think we're fine to skip them. I'll
Okay.
just move towards the last slide that we have, because the whole discussion and the whole options that we presented are fully open source. And I think whereas it's easy for organizations to just simply take them from the internet, often organizations who run machine learning projects in production, AI leaders across the world and across different industries, they choose collaborating with us on such use cases because of the security maintenance of the packages underneath. And that is important because otherwise you put your risk your workloads, your tooling, your data, your models, and that's something that no one wants. So ensuring the security maintenance of the tools that you use underneath is crucial. But then also, if I think of all the names that we dropped in this call per, it's important to ensure the integrability between all these tools. And I didn't focus today, but this is one of the biggest challenges that we see on the market, that there is a clear tool fragmentation that we clearly solve. And then if I look at our history for how long we have been investing in Kubernetes, Kubeflow, but also our strong partnerships that we have these days, we do have dedicated experts to support you with your machine learning workloads, as well as with the optimization opportunities that we have. We have workshops, we have tools that for which we provide security maintenance, enterprise support, or managed services that are worth mentioning here as well. And I think that's a wrap, mostly because we are running out of time. But please, let's see if we have any questions actually in the chat that we could answer, Perk.
Yep, that would be great. Thank you.
If I look at this, we actually have a couple of questions. So I'll start taking the first one, which really says, what are the best certifications to get started at Canonical? And when it comes to machine learning and data science, what I would encourage users to do who are just getting familiar with the project and with the product is take a look at Data Science Stack. It was released in general availability yesterday, actually, and it's a great tool that runs on micro-K8s, actually. To get you started, it runs on any workstation. If you have GPUs, even better. I see there's another question on Kubernetes work. Should we take that one?
Yeah, there are a couple of questions around Kubernetes itself, and I think we covered the webinar. But let me reiterate just a little bit. So there's a question about the design for the Kubernetes cluster for large-scale distributed ML training, right? And the GPU and TPU resources. So like we said previously, it would need to be a couple of things at the same time. It would need to be a design on the level of the jobs themselves, on the how do you run those on top of your Kubernetes clusters. Right? So first one is the paddle network. Then you have the Armada layer, right? So you would need to take care of those. There's also an interesting question about the multi-tenancy in Kubernetes, and yeah, it's a fair question because the resource isolation and security, it's all important things there. I think what you can really do there is that you for real multi-tenancy, I don't think we can really say that the usual thing that you would do, which is the namespacing, would work here. I would rather say that I would go as far if we need like a truly multi-tenancy as to go with the Kubernetes, the different Kubernetes clusters. That means the then you would obviously need to use the Armada on top of that to run your jobs. If you would like to match them together into a single Kubernetes offering. But other than that, I would just go with different Kubernetes.
I see.
There's also, yeah, come on.
I was about to say, I see there's another question around bare metal actually, and the configurations that are needed to this. So when we look at bare metal, actually when we look at MAS, it's really used for provisioning, and it's agnostic of the hardware utilized underneath, which is maybe one of the important pieces of information. But when it comes to configurations, I would strongly encourage you to go on MAS documentation on one hand, and then if you have additional questions, don't shy away from reaching out to us through the contact forms or on Discourse, because it would be probably easier to have one of our experts answering directly. However, it is important to mention that Kubernetes is enabled on MAS. Canonical Kubernetes is enabled on MAS, and it's one of the common architectures that I see on the market.
Yeah, exactly. So that would be also the I think the answer for the fault tolerance, right, and the self-healing. As for the strategies for deploying and scaling, managing the high availability ML, I think those are not very different from the Kubernetes itself, right? Because at the end of the day, those are just workloads which will just serve your needs, whether that is a web page or your ML inference. It's really very, very similar. So I would say that standard Kubernetes techniques would apply here, actually.
There's another follow-up.
Sure.
Sorry, there's a follow-up question on the data science stack as well, which mentions that there are only 6 pre-configured images. That is true. By default, it comes only with a couple of images, but you can add any other image into the notebooks. If you will check the documentation, it's going to be easier there's a how-to guide on this topic. However, if you face any problems, again, you can just go on Discourse and drop us a message there. One of our technical experts is going to follow up.
Exactly. There's also, I can see that there is a question about the screenshot of, and I think it was asked at the moment when we talked about observability. So that was Grafana. Grafana is a great tool, open source tool for your to visualize your observability data, your monitoring data. It's a part of the Grafana stack, and we highly recommend it. It's a software that Canonical uses as well for our Canonical observability stack.
I was about to say that I think on the screen we had Grafana and Prometheus. We had Prometheus for alerting as well, and then if you look at Canonical observability stack, we also have Loki enabled for logs, which is again extremely useful, especially if it happens or if troubleshooting is needed. And whether we like it or not, there are always going to be challenges and issues within a software solution that we will need to further look into. And I think we're running out of time, Perk. I see we have a lot of other questions, but maybe
Exactly.
we can have a follow-up webinar on some of them, or based
some
on
point,
some
yeah.
of them.
Especially that I can see that there's a question about the bare metal. Bare metal is like the whole another story, and it's not only AI related, but it's like a wide Kubernetes one. But that is true. Those were very, very good questions and very, very good sessions. Thank you, Andrea, for helping me out here.
Thank you, Bert, for joining and talking about Kubernetes for AI, and thank you everyone for joining us live. For any other question, feel free to reach out to us through our contact forms and on our website as well. Have a good day.
Have a good day, everyone.
Bye.